Hi, my name is Meng. I come from Rutgers University. Welcome to our work DeepTag. This is a joint work with New York University, NVIDIA, and SenseBrain Technology. In cardiac cellular MRI imaging, we usually generate a 2D image sequence covering full cardiac cycle to reveal the heart motion. We have untagged cili and tagging cili imaging. For TMRI, tags are intrinsic tissue markers, so it's a good standard for regional myocardial motion estimation. However, it could be very challenging due to the image appearance changes with the tag fading problem and motion as well as other artifacts. We first introduced the concept of motion decomposition and recomposition. For a material point M, which moves from position x0 at time t0, we have its trajectory xt. In the unframed sequence, we only record the finite M positions. We call the motion between time interval delta t as the inf motion, phi, and the motion between t0 and t-1 as the Lagrange motion, capital phi. We can say that Lagrange motion is the sum of the related inf motions. For motion tracking, if we set the first frame as a reference frame, our goal is to estimate the Lagrange motions. But for some frames, the Lagrange motion is so large that the estimated results could drift a nut. Since inf motion is always smaller than or at most equal to the Lagrange motion, we propose to track inf motions at first. Then, we recompose them back into the linear Lagrange motion. So we have two steps in our method. First, we estimate the inf motion field between any consecutive image pair by a bidirectional diffeomorphic registration network. Second, we recompose the inf motion fields as the Lagrange motion fields by differentiable composition layer. Motion tracking is done by predicting the position x-1 on later frame moved from the position x0 on the first frame with the Lagrange motion field. For the inf motion field estimation, we make use of the VAE model, in which we parameterize the inf motion by a latent variable z. We then let z be a stationary velocity field to introduce the diffeomorphism, and we can use a scaling and squaring layer to compute the linear inf motion phi from z. In a diffeomorphic registration framework, we can easily get the inverse inf motion by inputting mass d into the SS layer. We learned the posterior probabilistic distribution by the K loss, and the reconstruction loss term is actually a similarity loss between the warped moving image and the fixed image. Here, we use the negative normalized local cross-correlation metric as a similarity loss. We also penalize the gradients of the motion fields. Once we get all the inf motion fields, we can recompose them back into the Lagrange motion fields. As we showed previously, capital phi01 is the same as phi01. For n larger than 2, the current capital phi is the sum of the earlier capital phi and the inf motion phi. However, the loop position x-2 could be a subpixel location, and because inf motion field values are only defined at integer locations, we linearly interpolate the values between the four neighboring pixels. We designed this differentiable compositional C to finish motion recomposition. With the Lagrange motion fields, we can warp the first frame towards any other later frame and form a global motion constraint to further correct local inf motion estimation errors. From this table, we see that our method outperforms the traditional methods by a large margin. This is a view comparison. The image sequence contains 19 frames. Our method can even track the motion on the last 0 frames accurately, in spite of the significant image quality degradation. This is another video example. We extract the tag rate from the first frame and deform it by the estimated Lagrange motion fields. We can see that the warp tag rate can follow the underlying tag pattern in the images very well. More details could be found in our paper. Our code is available on the GitHub project page. Thank you.